All right, today we're going to decode the language of physics. We're talking about the words that describe every single journey you can imagine, from a simple walk down the street to a planet orbiting the sun. So, let's jump right in.
So I want to start with a really simple question for you. Just look at yourself wherever you are. Are you moving right now? You're probably sitting down, pretty comfortable, thinking, no, of course not. I'm sitting perfectly still. But are you really? Well, here's the thing. Even when you feel perfectly still, you are on a planet that's spinning on its axis and hurtling through space at literally thousands of kilometers per hour. So yeah, you are absolutely moving. And this gets us to the first and maybe the most important rule of motion. It's all about your point of view.
And that idea leads us straight into our first big concept. Motion is relative. To describe any kind of movement, we first have to agree on a starting point, something that isn't moving, at least from our perspective.
Just picture this. You're on a bus. To you, the person sitting right across the aisle is perfectly still, right? But to someone standing on the sidewalk watching you go by, you are both zooming past. So who's right? Well, guess what? You both are. It all depends on the observer.
So to solve this little problem, physicists use something called a reference point, or an origin. It sounds fancy, but it's really just a way of saying, hey, let's all agree on a starting line. It could be a tree, a house, the 0-kilometer mark on a highway, anything. Without it, trying to describe a journey is pretty much impossible.
Okay, so we've got our starting point. Check. Now, how do we actually describe the journey itself? Well, it turns out there are two completely different ways to tell that story. There's the long, winding path you actually took, and then there's the direct route, as the crow flies.
Let's make this super clear with an example. Okay, so an object starts at the origin. We'll call it point O. It travels all the way out to point A, a full 60 kilometers away. Then it pulls a U-turn and travels back 35 kilometers, ending up at point C. Let's break down what that really means.
If this were a car trip, your odometer, the thing that tracks your total mileage, would tell one story. It would say, hey, you traveled 60 kilometers out plus another 35 kilometers back. That adds up to a grand total of 95 kilometers. In physics, we call this the distance. It's the full, complete path that you covered.
But if you just pulled out a map, you'd see a totally different story. You started at the 0-kilometer mark and you ended at the 25-kilometer mark. So in a straight line, you are only 25 kilometers from where you began. We call this the displacement. It doesn't care about the scenic route. It's all about the shortest, most direct path from your start point to your end point.
So here is the absolute key difference, right? Distance is just a simple number. It's just a tally of every single meter you traveled. But displacement is smarter. It doesn't just ask how far, it also asks where did you end up compared to where you started. It's got both a number and a direction. And this leads to a pretty cool brain teaser. Just think about it for a second. Is it actually possible to travel a huge distance? I mean, you could run a whole marathon and still end up with a displacement of 0? The answer is a big, fat yes. And that's our perfect lead-in to the next idea.
Okay, let's kick it up a notch. We've talked about how far, now let's talk about how fast. And you probably guessed it, just like before, there are two very different ways to describe it.
So let's meet Usha. She dives into a 90-meter pool, swims all the way to the other end, and then immediately swims all the way back to where she started. The entire trip takes her exactly 1 minute flat. Now, she was clearly moving fast, but how do we describe her motion with our new physics words? And this is where two new terms come into play: average speed and average velocity. You see the pattern here, right? Average speed cares about the total distance Usha swam, her odometer story. But average velocity? Nope. It only cares about her displacement, her map story. So let's actually do the math here. Her total distance was 90 meters there and 90 meters back, so 180 meters. Divide that by 60 seconds, and her average speed was a pretty quick 3 meters per second. But what about her displacement? Well, she ended up exactly where she started, so her displacement is 0. And what's 0 divided by 60 seconds? It's 0. Her average velocity for the whole trip was 0 meters per second, even though she was swimming like crazy the entire time. So far, we've kind of been talking about these nice, steady journeys. But in the real world, come on, we speed up, we slow down, we turn corners all the time. We need one final word to be able to tell the complete story of a journey. And that word is acceleration. Now, most people hear acceleration and they just think speeding up, right? Hitting the gas. But in physics, it's any change in velocity.
So yeah, hitting the gas is acceleration, but hitting the brakes, that's also acceleration. It's just negative. And get this, even turning a corner at a constant speed is acceleration because your direction is changing.
And you can really see this come to life on a graph. A steady trip, what we call uniform motion, looks like a straight, predictable line. But a journey with acceleration, non-uniform motion, that's where the line starts to curve, telling a much more interesting story of speeding up or slowing down.
This cyclist's ride is a perfect little two-act play about acceleration. In the first part, he starts from a dead stop and gets up to speed. His acceleration is positive. It's working with his velocity. But then he hits the brakes. See, his velocity is still pointing forward, but the acceleration is now pulling backward, fighting against his motion. That's negative acceleration. The key is that acceleration isn't just speed. It's all about the change.
So there you have it, distance and displacement, speed and velocity, and acceleration. That's pretty much it. That's the basic language we use to describe motion. With just those few words, you can describe any journey in the entire universe. So the next time you see a car driving by, a bird flying, or even a leaf falling from a tree, ask yourself, what story is its motion telling me?